Hi, my name is Jordan Bramble and my teammates are Harold Marita and Ibsam Khan. Our senior design project is called The Design of a Quadcopter for winning the Jerry Sanders Creative Design Competition. First, I'd like to thank our sponsors, Bo Pollitt from Aurora Flight Sciences and George Mason University.
Thank you, Jordan. My name is Harold, and this slide is just showing you what we will gonna be talking about during our presentation, starting with the description of competition and ending with the simulation design. The Jerry Sanders Design Creative Competition is a yearly competition held at the University of Illinois, sponsored by Advanced Micro Devices. The objective is to compete with other devices by playing color cones onto pins to control territories, 2 airborne entries, and entire history. Here you will see an eagle-eye view of the arena with pin and cone locations. As you can see on the image on the right, you can see what the cones look like and their placements throughout the entire arena. The 4 different corners for 4 different teams are also marked. Here is a CAD diagram of all the arena and of all the territories. There are 36 first level territories which are marked in green, 8 second level territories which are marked in orange, and 1 third level territory which is marked in red. Now, competition rules. Each match will be 7 minutes long, consists of 4 or fewer robots, and the team's color cone is the topmost in a stack of cones for control of a territory. Teams cannot attempt to control a territory unless it will be contiguous. Airborne entries. Quadcopters cannot weigh more than 15 pounds. Rotors must be made out of plastic. Same battery rules apply as regular land entries, and quadcopter entries must contact the rules chairs with important and pertinent information. Scoring. Airborne robots have a constant 3-point multiplier when scoring cones. For each contiguous powered territory controlled at the end of the match, you're awarded 10, 30, and 40 points for first, second, and third level territories. The 3 mission requirements for the purpose of this project are as follows. The quadcopter shall have a greater than 50% likelihood of winning the competition and at least 70% likelihood of advancing the final round. The design requirements. The quadcopter shall be fit within a 3x3 foot cube, shall weigh no more than 15 pounds, shall be equipped with the first-person view camera, and shall be able to pick up the flying saucer cones. Here you see the traceability matrix, which relates all 3 mission requirements with all the design requirements and all of the competition rules. Here's a quick overview of the parts list. It gives you an idea of what everything is and where it's located on the quadcopter itself. There are a couple of high dollar value items which include the APM, which is the Autopilot Multi-Platform Module. We looked at 2 different quadcopters to see which ones meet our requirements best. We looked at one off-the-shelf quadcopter with AR drone and one custom-made quadcopter purchased through the DC Drones Group. The matrix shows the different specifications for each model. Here we have a weighted value matrix for the 2 quadcopters. We have 6 different categories for each category has a different weight anywhere from 0 to 5, 0 being not important, 5 being very important with the following attributes that we consider. For the experiments, we conducted a total of 2 experiments, one for the vertical, one for the horizontal velocity. Let's go over the horizontal velocity first. We tested 3 different distances, 20.5, 30.7, and 47.7 feet, running 36 trials. We used data and collected in the experiments to create distributions that will feed into our simulation. The tool we used to do this was the Arena Input Analyzer. As you can see from the horizontal velocity, 20.5 feet, we get a beta distribution. For the 30.7 feet, you get a normal distribution with a mean of 5.19 and the standard deviation of 0.975. For the 40.7 feet, again, we ended up with the normal distribution, but this time with the mean of 6.5 feet per second and a standard deviation of 1.09. Here's a short clip of the horizontal experiment.
Can you do one more?
For our second experiment, we calculated how long it takes the quadcopter to lift and stop at 2.5, 4.5, and 5.5 feet. We did 20 trials per distance and a total of 60 trials in total. For the vertical velocity of 4.5 feet, we got a beta distribution with a sample mean of 1.15 feet per second and a standard deviation of 0.268. Here's a short clip of the vertical velocity experiment.
Time. Begin discussing the simulation where we used our experimentally gathered data to model the time to acquire a territory using the equation shown below. The mu values represent random numbers chosen from our distributions. So the first problem we're addressing is that there's no current understanding of how a quadcopter will perform in this competition, and also there's no ideal combination of battery type and motor size to give the optimal results. So those are the two problems we're trying to address in this simulation. We're also assuming that teams will attempt to enter the third territory as soon as possible and that teams' paths will not come in contact until level 2. Also, no team will sabotage any other team, and we're assuming that cone transportation is normally distributed and takes about 30 seconds. So here's a breakdown of our simulation. Our expected performance simulation is done in Python, passing in our distribution data and outputting a distribution of points scored. The optimal configuration is determined in MATLAB and performs a trade-off analysis of different combinations. Here's our simulation diagram. As you can see, the distributions are being passed in. Territories are held in a priority queue that's self-updating to always find the nearest territory and the nearest cones to pick up. And then points are outputted. So the SciPy library is used to determine the time from each cone to control the next territory. Controlled cones accumulate points according to the competition rules, and there's a chance of opponents capturing a controlled cones which would affect your ability to score points. So here's our results over 111 simulation trials. Mean points was 555 with a standard deviation of 155, and as you can see, the data is normally distributed. So in this year's competition, the highest round score was 932 points, 430 points for second place, and the winning team averaged 866 points. So this gives us an 80% chance of runner-up, but only a 2% chance of victory. Here are our equations of motion used in the component trade-off simulation. We're computing a ideal RPM or average RPM using an average thrust. From this, we can determine the power using power coefficients given by the manufacturer, which gives current, and that relates to the battery capacity and will give us our flight time. So as you can see, 4 of the different alternative combinations meet the required flight times, and based on our results, the 1100 kV motor with a 10,000 milliamp battery provides the longest flight time. Even though the 850 kV motor actually yields more flight time, but it demands a higher voltage to do so. So the 1100 is our best bet for motor combination. In order to win this competition, a mechanism needs to be designed that can pick up cones quicker and can reduce that standard deviation, ideally get it down to about 6 seconds. Also, autonomy should be implemented so we can have a 5x point multiplier instead of 3x point multiplier.